One of the other questions that I've been getting when it comes to algebra is, why can't we add x squared terms to x's? Why can't we think of x cubed as being the same as x squared? And I want to try and explain what's going on here. If we have a term x here, let's say that x is a piece of string or a little bit of wire. This could be different depending on whether we make a long wire or a short wire. Let's say we have a length of wire x, and then I actually have 4 of these lengths of wire x, and I actually make them into a square shape here. If I'm to take the area of this square, I would be working out what x squared was. X times x would be the area of the inside of this square. And that's what I'm calculating when it comes to x squared. The area inside the shape that is built from the length x. So this x squared, this area, this surface, has actually nothing to do with the original x, apart from the fact that they happen to have the same length of the sides. But x squared, an area, a surface, can't be confused with the letter that's just x. In the same way, what would the number x cubed be? Well, if I was to take this wire and change it so that I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bits of wire and put them all together to make a cube shape like this. Whenever I now talked about the term x cubed, x times x times x, I'd be talking about a volume in the whole of this cube. I'd be talking of the volume of the cube. So the volume of a cube is not related to the area of this square, which is not related to the length x, apart from the fact that x happens to have the same length. So you can't add cubes to lengths. You can't add volumes to areas. They're different dimensions and different things. And that's why it's so important that you must never try and add x squared terms to x's. Think of x as being a length of a piece of wire, x squared as being an area, x cubed as being a volume. You need to keep these different terms together. So if I was going to look here and identify my x terms, here I have an x, and is there anywhere else I have an x by itself? No. So my simplified form of this equation would have 1x. It would have one length dimension of length x. I can have a look in this expression and say, do I have any more length directions? Well, yes, I have a y length here. And notice it's a different length to x. So I have a length y. Where do I have that? I have 1 over here. And I only have 1, so I can't simplify over either of those. I don't know how big x is, and I don't know how big y is. They are variables. They could be any number. Okay. What else do I know? Well, let's take our, do we have any area terms in x? Do we have any x squareds? Well, we have 2 area terms, 2x squared here, and we have 3x squared here, plus 3, and we have another x squared term here. So these are all the area terms involving x. And how many do I have in total? I have 2 plus 3 is 5, plus another 2 is 7. So I will have 7 lots of area terms. It's like me taking 7 of these and putting them after one another in a row and saying, how many do I have? First I had 2, then I added 3x squareds to them, and then I added another. So if I was to count up the amount of area of x squared I have, I would have 7. And it's not related to the length x of my piece of wire. So that's what we're doing there. Now we've multiplied or added all our x squared terms. Do we have any y squared terms? And what is y squared? Yes, we do have a y squared term. And just like x, it's an area term. It's the length y, which is different from x. We don't know how big it is. It is y times y. This is going to be our area term of y squared. And we only have one of them. So we've now worked on the y terms. Oh, whoops, look here. I missed an x term there. We had an x plus a 2x up here. Sorry about that. So we should have had 3x here. We have one piece of wire plus another 2 afterwards, so we end up with 3x. That's why it's very good to underline here, because you soon see if you've missed something. Okay, now we've done our y's, our x's, our x squareds, our y's, our y squareds. Do we have any x cubeds here? Yes, we do. We have one x cubed term here. So we have one volume of length x and a volume term in x cubed. It's not the same as an area term, it's not the same as a length term, so it has to be kept separately. So we would add our one x cubed term to our equation here. Okay, now we've finished with x cubes. We have something else over here. What is this? 5 lots of xy. Well, xy would be made if we took the length of the wire x and had 2 of them, and in between we took the length of the wire y and had 2 of those. The area of this rectangle, and because x and y are different, it's going to be a rectangle, would be xy. So an xy term, one xy would be one rectangle. 5 lots of xy's could be thought of as being 5 rectangles of this size, xy. So what do we have there? We only have one of those, 5xy. And then we're pretty much finished, except we've got a few little numbers here at the end. We have a 5 plus 5 and a minus 1. Plus 5 and minus 1. And these are absolute values. 5 minus 1 is 4, so we end up like this. In maths, it's usual that we actually write our cubed terms first. So I'd rearrange this equation to have first x cubed plus, so I've done that one now, plus my next set of terms would be 7x squared. And then I'll do my other y terms as well, put in my y squared, so that I've done that. Then I have some terms that are x, y together. I would put those after. Why? Because what I'm doing here is I'm keeping my volume terms together. All of these terms here in the middle can be thought of as being area terms. So I'm keeping them together. This can be thought of as being a volume term and keeping it together. All of these were areas. Here's my x squared, here's my y squared, here's my xy. Plus my length terms. Here I have 3 lots of x plus a y. So here I'm keeping all my length terms together. And then I'm finishing it off at the very end with the values of numbers that I have. Okay? So here we have the numbers. So you can't just add all the numbers together, they represent totally different things. Length x, length y, area y squared, area x squared, volume x cubed, rectangle xy. And you can't add them up, you must keep them separately. But this method of underlining or crossing out to make sure that you haven't missed any of the terms here makes that your final equation, even though it looked quite complicated, and it's still quite complicated, this one is now much simpler than that one was up there. Because here we had 5 minus 1, and we know what 5 minus 1 is. We know that x plus 2x can be simplified to 3x. So whenever we see terms that are of the same sort, we are allowed to add them together. And this is very important in algebra. You must only add, and we call it adding like terms. Add like terms. So in order to be able to add 2 terms together, they have to be of the same form. I can only add x squared terms to other x squared terms. And there are 3 x squared terms in this expression. So I can add 2x squared plus 3x squared plus 2x squared. But I can't add x's to that because they're totally different. Okay? And I hope that this will make it clearer to you how to simplify these long strings.